time to wake up. It's time to wake up. It's time to wake up. It's time to wake up.
Let's first have a look on the deviation of the final energies of sectors. We have around about 30% of our energy we use for home, where we're living. 27% for industry, for products we need. Of course, we want to travel, around about 30%, and 13% some other stuff. What is the main application using this energy? This is HVAC. What is this? Heat, ventilation, air conditioning. We want to have warm houses, and we want to cool rooms like this. This is around about 34% worldwide, a very huge part. Cooling is only possible with heat pumps called chillers, and heating is mostly today done by fossil energy. But everybody think when we change also to heat pumps, this part would decrease. But this isn't not true. Because of climate change, we need much more cooling, and therefore much more chillers. I say conventional heating and cooling is proven but inefficient. Why? We have to transfer heat from the left to the right, smile, from the left to the right, and mostly we have one part air, this room, and we have to transfer it also to the environment. It's also air. But how it is done in the last century? First, it is transferred to water, then to a refrigerant, where the temperature increase take place, then to glycol, and at the end of the day, then to air. The transfer is done by heat exchangers, which are very inefficient, and also every circuit needs energy. And the main thing is a value called epsilon. This is for efficiency, which means this is the relation between the transferred heat versus the used energy. This is less than 2. Sounds good. Maybe when we try to cool a data center with 100 kW, you need, by a factor of 2, 50 kW. But physical law allow factors of 20, 30, or much more. What was wrong? Can we improve it? No. Engineers did this for nearly 1 century. What can we do? Skip it away. Let's step back to the start. Wouldn't it be nice if of both sides we have air, connect it with the heat exchanger, and need much less energy? Is this possible? Yes. When we think about such concepts, we get efficiency around about of 10, 5 times better than today. Why we don't have it today? Because we need a fractal heat exchanger. What is a fractal heat exchanger? This is, I think everybody knows since COVID that when we breathe, we have one stream, and it is divided again and again in a million micro streams until the air reaches the pulmonary alveoli. Why it's such complex? Why we then have round about half a football field of area inside our body in a very dense volume. And why such a huge area? Because this is necessary for the gas exchange. And the same is true for heat exchange. Tina will show us how this can be built also technically.
Right, so now we have heard how the principle works when it comes to the physics, but of course now it's the time to talk about 3D printing. So we have more or less printed a lung, which of course doesn't look like a lung, but it looks like this. So you see here a super, super fine structure printed in steel or whatever material you need. And I want to bring you in the world of 3D printing and show what's possible already. So as Holger has already mentioned, it's necessary to print really, really, really fine structure, which you can see here on the picture. And to get a better idea of the whole part, you can see it here. So on the bottom, it's the building plate you have here, but then this is the part we have printed with a super fine structure. And also, of course, we have bring a part of that part with us, which you can see here. So that's the position where the air comes inside. That's part of the heat exchanger. And then when you turn it around, and hopefully I don't crash all the bottles, then here the magic happens. So here is where we have like super, super fine channels printed, and everyone is invited to come to us after the presentation and have a look on the part, and also visit us, of course, at our booth in the other hall. So this is what we're talking about today. And I want to give you an impression who we are and what is EOS and our purpose about, which is responsible manufacturing. And this is why I've brought a video with us. Actually, I'm a bit curious how the sound will work, but I will try.
To upset building this balance by being restrictive, wasteful, and inefficient. We can do better. We believe that with innovation and technology, we already have the means to meet the needs of modern life while doing less harm to our planet. That is why we are determined to accelerate the world's transition to responsible manufacturing, creatively, conscientiously, responsibly. Our approach at EOS is to extend the boundaries of manufacturing ingenuity. We pioneer additive manufacturing technology because it is responsible by design, offering on-demand and distributed production, rapid idea iteration, customized products, and lightweight design. We nurture an ecosystem and empower everyone here at EOS to strive for results that increase energy efficiency, reduce waste, and use resources conscientiously at every step of the process. All of these come together to establish responsible manufacturing as the new normal. Now is the time to transition from theory to reality. All of this is possible thanks to the commitment, knowledge, and ingenuity of everyone at EOS. Responsibility matters.
So just as an introduction, why we talk about responsible manufacturing. And before we continue to talk about our path and the heat exchanger we've printed, I just want to get a couple of steps back with you, because I have no idea if you already know what industrial 3D printing is and how the technology works. And this is why I want to share you some impressions about our company, about our great technology, and we start here. So when we talk about 3D printing, sometimes people think about FDM, where you have these little rods which you put on a plate. But we have also this kind of 3D printing, where the feedstock is a powder. The powder can be plastics, polymers, or metal powders. Today we talk about metal powders. We have also the polymers. And it's important to understand the principle, because we have really, really fine powders, and you need to think in layer by layer. So you put one layer of powder, and then you need the energy to melt the powder exactly on the spots where you want to create the part. And then we have a laser to bring the energy into the material. and the laser is melting the material on point where you want to create the part. And then the next layer of loose powder is coming, and the laser is coming again. And that's the principle, how you create a part layer by layer. And we talk about like super thin layers, about 60 microns or 40 microns. That's one layer. So you can imagine how many layers you have in that big part and how long you build that part. And it's not only about the machine we're talking about, we talk about the material and about the process and the parameters. So it's a complex system that we are able to create that part. And with that slide, I want to give you an idea how 3D printing and responsible manufacturing works, or how you have different pillars to be responsible. So when I talk about purpose-driven design, then this is exactly an example what we call purpose-driven design. So we look on the purpose, on the function of the part we want to create, and coming from the purpose, we create a bionic structure, the structure which is optimal or best for the solution. The second pillar is customization. And this has nothing to do with that. I just want to share it with you to give you an idea what is possible with that technology. And I've brought a different part, so little jump to the side of a different topic. I've brought some glasses with me, and you can also print glasses. And these glasses are not normal glasses, no, they are customized. So you can scan your head, and print out the glasses made for your head with that skin. Then on-demand decentralized production. I always brings an example from my former company I was working for, which was the German Railways. And the German Railways, they have a lot of spare parts in their warehouses, and it's nice to have the spare parts, but the problem is that they produce more spare parts which they need, or they do not have the spare part they need. So the perfect word would be to have a digitalized warehouse, and that you can just print out on the spot where you needed your part. So that's the idea behind the third circle. And then, of course, circularity. And circularity is more than we talk today about that part. It's also about to have responsible materials, to reuse the powder in the circle, and to have a responsible process. And I've already mentioned we have the possibility to print plastics, but also we have the possibility to print metals. And I just gave you a rough overview what is possible to print. So you can print different aluminum alloys, you can print steel alloys, and in Germany I would say the Königsdisziplin, so the high level of printing is printing copper. This is also very interesting for other applications like heat exchangers, and it's possible with our technology. And if you have now still not again in your head the picture of this small hobby printer, then this is how our printers looks like. It has a footprint of like 4 meters, squared 4 meters, and then a building chamber of 400 across 400 millimeters building platform, and you can print big parts like that. So I hope I have give you a little impression what is possible with 3D printing. If you have more questions, then of course come to our booth. And now I would hand over to Holger, talking a bit more about our application here.
So, having this fantastic technology and the cooperation with the world technology leader, we started a joint development, and in this cooperation it was able to manufacture this missing link for the air-to-air direct heat transfer. What you can see here, it has a high round about 1.5 meters and a shape of round about half a square meter. You must not understand how it works in detail. We have inside there is a so-called turbo machine, which compresses the air, some heat exchangers, as you can see here, and nothing else. What is the most important thing? That the air we want to cool is at the same time also the refrigerant. So we don't need refrigerants like FKW or something like that, responsible for the global warming factors and so on, responsible for our carbon footprint. And we have an efficiency roundabout of 10. And this is possible today, not in the future, due to such a very fantastic technology. So what does it mean for us if such a chiller or heat pump can be placed in the market? Market entry will around about in 2 years. Of course, when we are more than a factor 5 better, we have a reduction of around about a little bit more, 80% for the energy needed to run the machine. Of course, we have also then 80% reduction of carbon footprint. What does it mean for a country like Germany for reduction of CO2, where we all talk about? This is in a country like Germany. These are 80 million tons. This is a huge amount, more than 10%, which a country in which Germany put into the environment every year. And for the planet, we have today a gap of 22 gigatons worldwide, and this technology could close the gap by 4 gigatons. Round about 20% of the gap open of the Paris Protocol and what is needed to get to net zero 2050. So, Tina, it's your part.
That one maybe, yeah. Okay, yeah, so I hope we could give you an impression about the technology and also about the chance we have with that technology to save carbon emissions. And if you want to learn more, then you can come to our booth. As I've already mentioned, we are in the hall where the big stage, the main stage is, close to the Audi and DB booth. It's the booth CO5, and you are very warm welcome to talk with us, to come and join and learn more about the possibilities of the technology. Thank you so much.
Thank you so much. I have a question. You were saying that the power consumption is being reduced by 80% during running the system. But what about the production phase? You need energy to produce your device, you need metal, you need other resources. Then the whole device has to be maintained over 10 or 20 years. Again, you will use materials, resources, and power for maintaining the device. And then, after the lifetime of the device is finished, it has to be discarded. Again, CO2 is released. What about this? Please give us the whole picture.
I have the. Thank you for your argument. Thank you for your question. This 80% reduction is included. It includes the carbon footprint of the supply chain. You're right. Today we don't know which carbon footprint will occur when, after end of lifetime. But over the whole phase, including the production, we have more than 80% of power consumption. Not only when running the machine.
More questions? Okay, then thank you again, and we can continue the talk. Thank you. Bye-bye.
It's time to wake up.